Hello everyone. Alright, last video in periodicity chapter 10. And the two concepts they bring up is ionization energy and electron affinity, and then we'll talk about multiple ionization energies. Alright, ionization energy, the energy required to remove one electron from a gas atom. Why does it have to be a gas atom? That's important in the definition. Because if you have solids and liquids, the particles are right next to each other. So let's call this atom A and this atom B. And they're right next to each other. Can the nucleus from atom A also attract the electrons from atom B? And the answer is yeah. We can attract those anytime a positive is near a negative. So when you're dealing with a liquid or a solid, you can't really measure ionization energy. The particles have to be spread out so that one particle is not assisting the other and holding on to the electron. So in order to get this measurement of getting rid of it, how much energy it takes to form a positive one charge, then it has to be in the form of a gas atom. So again, what is ionization energy? More or less what it takes to create a positive one charge. We're going to try to get rid of one electron. All right, so now we got to go back to Coulomb's law if we're going to predict the trend here. Force is equal to Q1, Q2 over D squared. Okay, so which atoms are going to be difficult to remove electrons from? Well, if we look at the numerator in terms of a period trend, it's going to be really difficult to remove electrons from substances that have high Z effective force. So the more protons you have, the more difficult it's going to be to remove that electron. So if we look at the periodic table, oh my gosh, that is the worst one I've ever drawn in my life. Okay, if we look at the periodic table, that one's not much better. Okay, I just can't. Sorry, that's got to go. I can't do that. That's just wrong. Let's try it again. Okay, a little better. All right, so as we go from left to right across a period, we're not changing D squared, we're only changing Q1 and Q2. So the elements on this side of the table we're going to call electropositive. That is, they tend to form positive charges. And then the elements on the right side we're going to call electronegative. They tend to form negative charges. Well, why? Well, as we go to the left, we have low Z effective force. In other words, we have a weak nucleus. But that force increases as we go to the right, where we have higher Z effective force. So the energy to remove an electron from something with a low Z effective force, there's not much energy required. That's why we call them electropositive. So in terms of ionization energy, let's call it IE. It's going to require a low amount of energy on the left side and a high amount of energy on the right side to overcome that Z effective force. So the trend is, as you go from left to right, ionization energy increases. Okay, so if we look at ionization energy, we would say in period 4, we'll start with potassium. Potassium is going to have less ionization energy than calcium, which is less than scandium, and then we go all the way across, and we would expect bromine to have the highest ionization energy in period 4 because it's furthest to the right and it has the highest Z effective force. If we look at the group trend, well, now we're dealing with D squared. All right, so as we go from top to bottom down any particular group, we said that this is still governed by Coulomb's law, Q1, Q2 over D squared, but I said focus on D squared when you're looking at a group trend. The more energy you have, the farther away the nucleus is. So when D squared is large, that equals weak attraction. weak attraction. Okay, so as we go down the group, you're getting more and more quantum energy. The electron is getting further and further away from the nucleus, and it's becoming easier to remove it. So the trend as you go down the group is that ionization energy decreases. It increases left to right due to Z effective force, but it decreases as you go down a group. So, again, the term ionization energy, and then we're going to rank things. Hydrogen versus lithium versus sodium versus potassium. As we go down the group, it gets easier. So ionization energy is going to become less as we go down the group. Okay, so again, we go to our notes here. Ionization energy decreases down a group, we said, because more quantum energy, further away from the nucleus, large d squared, easy to remove an electron. But it increases across a period because you're not changing the quantum energy in that level. What you're doing is you're just adding more protons as you go from left to right. Therefore, you're increasing the Z effective force, and it's becoming more and more difficult to provide enough work energy to overcome the attraction between that strong pulling nucleus and those outer electrons. Now, ionization energy, they kind of bring in this sub-level effect. And it's a good example of when we say periodic trends, that these are trends. There are plenty of exceptions, but even with the exceptions, we can kind of predict where the exceptions are going to be. So we said, for instance, the factors involving ionization energy is nuclear charge, so Z effective force. And we said that that's mainly when we're dealing with a period trend. And the radius, which is created by the amount of quantum energy in the outermost electron, is what we refer to when we're talking about the group trend. But I did mention in the other video something called the shielding effect. Now, the shielding effect is where the core electrons repel the valence shell. So they're going to mention that when they talk about ionization energy. But lastly, the bigger thing is they're going to talk about sublevels and how sublevels affect the values. All right, so we already talked about Z effective force and how that affects ionization energy. And we already talked about the radius. The greater the atomic radius, the larger d squared, the lower the ionization energy. But we didn't talk about shielding effect. Again, and this is a complicated topic. It is a sort of topic I studied in my second year in college. Not all electrons are equally shielded. So I'm going to simplify this and just say, look, the core electrons, they create electron repulsion, and so it repels the outer electrons. And so the valence shell winds up further away from the nucleus than what you might normally expect. But the truth of the matter is it's a complex physics topic, and really something that we don't even get into much at the AP level. I mean, we do talk about shielding in general, but we don't talk about how each electron is shielded a little differently. So for now, I think it's okay to just think of, again, as the core electrons actually produce negative charge, and they repel the valence electrons, which are also negatively charged. But the big thing is this sublevel effect. We can predict where we're going to get exceptions to the rule based upon looking at our sublevels. If we have half-filled shells or full shells for ionization energy, those are particularly stable. And if something is stable, it's going to take a lot of energy to change it. So when you look at P3 or D5 configurations, or D10 for a full sublevel for a D shell, you're talking about additional energy required to remove that electron. So let's take a look at the trend in terms of the second period. All right, so we'll write ionization energy, second period, atoms. All right, so we start way to the left. Lithium is going to have the least amount of ionization energy. Sorry about that. And so it's going to be lower than beryllium as we move to the right. That makes sense. Now we're adding, takes more energy as we move to the right. So boron will require more energy, and then carbon, and then nitrogen. However, when we get to nitrogen, it actually takes more energy to remove an electron from nitrogen than it does oxygen, even though oxygen is further to the right. And then it goes back to the trend again, where it takes more energy to remove an electron from fluorine than oxygen. So the question is, well, why? If you look at the nitrogen configuration, it's a P3, and that's a half-filled shell. So it takes a little bit of extra energy to disturb that system and to remove the electron. Okay, last trend is electron affinity. Remember we said ionization energy, if you're dealing with a gas atom, it's the amount of energy to remove one electron, so to form a positive one charge. So electron affinity is pretty much the opposite of that. What we're going to do is we're going to take a look at the atom's ability to attract additional electrons. In other words, if you're attracting an additional electron, you're forming a negative one charge. Affinity means to like something. It's a bit of a misnomer. Nuclei don't like electrons. They're attracted to electrons because of their opposite physical forces. All right, so metals have low electron affinities, nonmetals have high electron affinities, and the trend is electron affinity increases as we go across a period, and it decreases down a group. Why? Well, the same reason for every other trend. It increases from left to right because you have more Z effective force, and therefore it's easier to attract electrons when you have a very strong pulling nucleus. And the reason why it decreases as you go down, because the outermost electrons are so far away because they have so much quantum energy, that d squared is large. And if you can't attract your own electrons, how on earth are you going to be able to attract electrons from other atoms? So let's take a look at this trend in a little bit more detail. So again, here's our periodic table. All right. Terrible again. And we're going to call this electron affinity, right? Abbreviated EA. And electron affinity decreases down a group, and it increases left to right across the table. This very wide table that I drew. Okay, so again, if we were to rank things going down the group, Group 1, hydrogen, lithium, top to bottom, sodium, potassium, rubidium, cesium, francium. Well, electron affinity decreases, so we would say that hydrogen's electron affinity is greater than lithium, greater than sodium, which is greater than potassium, rubidium, cesium, and francium. In fact, hydrogen, which normally forms a +1 charge, can also form a -1 charge if it's part of what's called a hydride. And then we said electron affinity, this is for the group trend, sorry. For the period trend, we go left to right. We'll take a look at the the period 3 elements, sodium to the left, then magnesium, aluminum, silicon, phosphorus, sulfur, chlorine. And again, although there are exceptions, we would expect this trend that the electron affinity increases as we go to the right. Last topic. Multiple ionization energies. We talked about ionization energy being the energy to remove one electron and form +1 charge. But what if you have to remove a second electron to get a +2, or a third electron to get a +3? Well, we can predict the energies relative to each other and then make a prediction about what material we're using depending upon where those electrons come from, whether they come from a valence shell, which would be low energy. It's very easy to remove an electron from a valence shell because those electrons are unstable. But what if you're trying to remove an electron from a stable core? Again, it's going to take a lot of extra energy to do that. So if we're comparing the multiple ionization energies for aluminum, magnesium, and sodium, let's go ahead and do that. Let's create a chart. All right, so we have sodium, we have magnesium, we have aluminum. Let's do the electron configuration for each. All right, sodium is a neon core 3s1 configuration. Magnesium, same thing but 3s2. And aluminum, same thing but 3s2, 3p1. Alright, so let's set up these columns. First, ionization energy. In other words, we're going to make it a +1. Second, ionization energy versus third ionization energy. Alright, so if we're doing the first ionization energy from sodium, we have to say to ourselves, well, where is this electron coming from? We're going to take it from the valence shell, so that should be very low energy. In fact, what you're leaving behind after you create the +1 charge is sodium with a neon core, which is stable. However, if you go to produce sodium with a +2 charge, where does that electron come from? Well, that second electron has got to come from a core. That's going to take a tremendous amount of energy. So this is going to be very high energy to remove the second electron, because what we're doing is we're breaking up that neon core and we're leaving behind helium, 2s2, 2p5. Let's zoom in on this a little bit. And then finally, the third ionization energy. Again, this is going to be high, not as high as the second one. But this is going to be high energy because, again, where is that valence electron coming from? It's coming from this valence shell, but isn't sodium a lot closer to adding an electron and completing its neon core? So it's going to fight you on this. It's going to want to complete the neon core, but yet you're pulling off another electron in order to produce a +3 charge. So that's going to be high in energy as well. And we leave behind helium, 2s2, 2p4. And so the trend is, if we record these results, we're going to have a low value for our first ionization energy and then high values for the second and the third. For magnesium, going to be slightly different. The first one and the second one are going to be very low energy. Well, again, why? Well, where are those two electrons coming from? They're coming from a valence shell. So if you create the magnesium +1 ion, you get neon core 3s1, and then if you create the magnesium 2+ shell, you just leave behind a neon core. And then finally, we're going to see a big jump in energy when we go to remove the third electron, because now that third electron has to come from a neon core. Okay. So what would we predict then for aluminum? We would predict that the first, second, and third are going to be low energy, because all of them come from the valence shell. First one we lose is a 3p, and then we lose our 3s's, our 2 3s electrons. All right, aluminum 2+, neon core 3s1, aluminum 3+, just the neon core. So we can take a look at data, and it might look something like, you're going to see a large jump. If we put data on a table, like, I don't know the exact values in kcals or in kilojoules, but let's say, for instance, if sodium was 400 for the first ionization energy, it's going to jump to like 2,000 something for the going to jump to 2,000 something for the second ionization energy, and then it's going to continue to go up for the third ionization energy. Either way, it's going to be much higher than the first value. All right, that's chapter 6 and 10 on periodicity. Thank you very much.